students, welcome to this lecture on advanced semiconductor devices KEC 056. This is lecture number 4. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. So, in this lecture we will continue our discussion on carrier concentration in semiconductors. Okay. So, in last lecture we started our topic of carrier concentration in semiconductors, okay, especially at thermal equilibrium. And when we say thermal equilibrium, we are referring to a condition where only thermal energy is available to the charge carriers. There is no other biasing or photo energy applied to the semiconductor. Okay. We had arrived at two expressions, one for number of electrons per unit volume in conduction band. Okay. This is denoted by n and equal to n subscript c e to the power minus E c minus E f by k t, okay, where N c is effective density of states in conduction band. Okay. E c is start of your conduction band, minimum energy level in conduction band, and E f is known as Fermi level energy, k is Boltzmann constant and T is temperature. Okay. In addition to this, we arrived at another expression which is number of holes per unit volume in valence band. Okay. This is denoted by P and given as N V e to the power minus of E f minus E v over k t. Okay. And here N v is the effective density of states in the valence band and E v represents the maximum energy level inside the valence band. Okay. So, this is where we concluded our previous lecture. Let us proceed further. Now, we will use these two equations as our basis for further analysis. Okay. So, we have an equation for electron concentration and we have an expression for hole concentration. Always remember the free electrons which are available in the conduction band and the holes which are available in valence band, these are your charge carriers. Okay. These are the ones which contribute to current in any semiconductor device. Okay. So, this is equation number 1 and this is equation number 2. I want to estimate how many charge carriers per unit volume are available to me in a intrinsic semiconductor. Okay. So, that semiconductor which has not been doped with any trivalent or pentavalent atoms. Okay. Any type of an impurity has not been added, it is a pure intrinsic semiconductor, and I know that in an intrinsic semiconductor the number of electrons which reach from valence to conduction band, they leave equal amount of holes in the valence band. Okay. So, the number of electrons per unit volume in the conduction band is equal to number of holes per unit volume in the valence band. So, I can say that in an intrinsic semiconductor or in a pure semiconductor without any doping, N is equal to P. Okay. For this, I also use another law which is known as law of mass action. Okay. What this states, now this law of mass action is valid for both intrinsic as well as doped semiconductor. So, whether doping is present or not, law of mass action is valid. What it says is that the product of carrier concentrations, electron concentration multiplied by hole concentration is a constant number given by Ni square. Ni stands for Ni resembles intrinsic carrier concentration. Okay. So, if I multiply equation number 1 and 2, if I multiply 1 and 2, I am going to get N dot P equal to N c N v, exponential terms add up. Okay. So, I will have minus of E c minus E f plus E f minus E v divided by k t. Okay. So, you can see here that E f will cancel each other and I will only be left with minus of E c minus E v. This is N dot P, this is obtained by multiplying equation number 1 and 2. Okay. So, this according to law of mass action, N dot P is nothing but equal to square of intrinsic carrier concentration. Okay. And this term is equal to this term which is written here. If I take square root now, I will get this expression here. What is this? This is the amount of charge carriers available per unit volume inside an undoped semiconductor. Now, this will also be equal to N, this will be equal to P. So, this many electrons will be available per unit volume inside the conduction band, and this many holes per unit volume will be available inside the valence band, and E g here in this equation is equal to E c minus E v. If you remember the energy band diagram, E c minus E v is nothing but the forbidden energy band gap. From this equation I can say that N I is directly proportional to exponential of minus E g, and N I is inversely proportional to the temperature. Okay. Or you can say that 1 by e to the power minus t you can also write. Okay. So, the idea is that those material which have lower band gap will have higher concentration of charge carriers. Those, if temperature is increased, the concentration of Ni is also going to increase. Okay. So, this should be this term here should be e to the power minus t. Okay. So, increase in temperature is going to increase the intrinsic carrier concentration. Similarly, reduction in E g is also going to increase intrinsic carrier concentration. Okay. Now, let us just see what is the effect of doping. We know that in pure semiconductors N is equal to P. Okay. But when doping is added, either you add trivalent or pentavalent atoms to your general pure silicon atom, you create an imbalance or a non-equilibrium such that after doping N is not equal to P. Okay. So, in an extrinsic or a doped semiconductor, your electron and hole concentration now will not be equal. Okay. There will be some kind of an imbalance in this. However, charge neutrality will still be maintained, which means positive charges will be balanced by negative charges and vice versa. So, whatever negative charge you have in the semiconductor, that will be balanced by the positive charges. Okay. So, let us see what is the effect on the energy band diagram. Suppose you add pentavalent impurities, your so called N type impurities. These are like phosphorus or arsenic which have 5 valence electrons in the atom. Okay. 4 of these valence electrons are going to bond with silicon and 1 will be left, and that electron is generally free and it tend to have higher energy available to it, okay, because it is basically acting like a free electron. So, for this, in the energy band diagram we know that we solved for potential wells and we found that closely spaced discrete energy levels or so called energy bands were formed. These extra donor electrons, they also have to occupy certain energy level, okay, and they being high energy, they tend to occupy certain energy level which is just above E c. Okay. So, the amount of energy required for these electrons to jump to the conduction band is very small, and that happens easily at room temperature also. So, we can safely say that at room temperature all the donor atoms have donated their extra 5th electron. Okay. So, these electrons from the donor state can easily go to conduction band. So, this is E c, this is E d, this is E v. E d stands for donor energy states. Okay. This is the energy state occupied by that 5th valence electron of the pentavalent impurity. Okay. And once they have reached the conduction band, they are said to be completely ionized, and after complete ionization E d is fully empty. Right. Same for trivalent impurities, those atoms which have 3 valence electrons. So, 3 of them bond with silicon and the 4th valence electron of silicon is also accepted by this trivalent impurity. Okay. So, it accepts an extra electron from silicon and creates a extra hole inside silicon. So, this is similar to addition of holes in the silicon semiconductor. Okay. So, these accepted electrons, because they are being accepted from a bond which was incomplete, so they tend to have lower levels of energy. So, the energy levels occupied by this 4th valence electron of silicon which did not find an electron to bond, that electron occupies an energy state known as EA or acceptor energy state. Okay. And this state is just above the valence band maxima. Okay. So, this is EV, this is EA and this is EC. So, these electrons in the valence band can very easily occupy these states. Okay. They can very easily occupy these states, and what they leave behind is holes. So, when you add trivalent impurities or p type impurities, you add a lot of holes in the valence band. Okay. After complete ionization, which means every acceptor atom has accepted at least one electron, EA is completely full, okay, and it leaves equal amount of holes in the valence band. So, here you see you did not touch the electron concentration, but you have altered the hole concentration. So, in this case P is greater than N. In the previous case, when you added pentavalent impurities, you have increased the electron concentration, but did not touch the hole concentration. So, here N is greater than P. Okay. So, that is why I said after doping an imbalance or non-equilibrium in carrier concentration is generated, right. Okay. So, this was the effect of doping on the energy band diagram. Let us just discuss what is meant by Fermi level energy. If I go back to the carrier concentration equation, you would see that both the equations involve EF. This EF is appearing in both the expressions, which basically means that my carrier concentration is directly or indirectly dependent on this value EF. This is I want to understand in more detail now. So, if I go through the Fermi Dirac function, which is nothing but the probability that an energy state whose energy is E has an electron is occupied by in that state. Okay. That is given by 1 by 1 plus exponential of E minus EF by KT. K is Boltzmann constant, T is temperature, E is that energy at which you are measuring the probability, and EF here represents the Fermi level or Fermi energy level. Okay. So, both the words are acceptable, either you call it as Fermi energy level or simply the Fermi level. Okay. If I look at this graph here, the y axis resembles energy and x axis is f of E, this function as a function of energy, an inverted graph. Okay. So, f of E is a function of energy, but this is sort of an inverted graph where energy is on y and f of E is on x. Okay. This has 3 elements. If you see this element here, this graph in red is at T equal to 0 Kelvin, absolute 0. Okay. There is another graph here which is at temperature T1, okay, and T1 is greater than 0 Kelvin. And third element is at this same graph is at another temperature T2, which is higher than T1. So, you can say that this is a function of temperature as well as energy, right. So, let us try to define now what is the Fermi level. In the Fermi Dirac function f of E, if here I put T equal to 0, okay. If I draw the energy scale, suppose this is EC and this is EV, just for discussion purpose I say that EF is somewhere here. Okay. So, if T is equal to 0, this term becomes 0 here, okay. This term is 0. So, anything divided by 0 becomes infinity, but it also depends on the numerator. If E is greater than EF, so all these energies above EF, that means E minus EF is going to be a positive number. In that case, I am going to get E to the power plus infinity. So, a very large number like infinity appearing in denominator, I get 0 as f of E. Okay. But if E is less than EF, all those energies which are below Fermi level, okay, in that case this term becomes almost equal to 0. So, f of E becomes equal to 1. So, at 0 Kelvin absolute 0, if E is greater than EF, f of E is 0, if E is less than EF, f of E is 1, okay, which means the probability of finding an electron above EF at 0 Kelvin is 0 and EF is the highest energy which an electron can have at 0 Kelvin. Now, since EF is below EC, it means at 0 Kelvin there will be no electron present in the conduction band. Okay. That is why we say that at absolute 0 a semiconductor behaves like an insulator, because there are no charge carriers available, and if no carrier is available there will be no current. Okay. Similarly, in this expression if I put E equal to E f, so this term here becomes 0. Okay. Irrespective of temperature, this term is now going to be equal to 1 by 2. Now, what does f of E measure? It measures the absolute probability that an energy state E is occupied by electron, and if it is equal to 1 by 2, it means the probability of finding an electron at energy level E f is exactly 50%. So, with these I can define Fermi level now. It is that energy level at which the probability of finding an electron is 50%, and at absolute 0 or 0 Kelvin, this is the maximum energy which an electron can possess. Okay. So, this is the concept of a Fermi level, and Fermi level directly impacts your carrier concentration. So, E f affects your carrier concentration. Okay. Now, let us identify where the Fermi level is actually located. In my previous slide, I assumed it to be somewhere between E c and E v. So, let us just see where it is exactly located. Okay. So, for an intrinsic semiconductor where there is no doping, this is my expression for electron concentration, this is for hole concentration. Okay. This is always valid. For a pure semiconductor, I have already said without doping n is equal to p. The electrons which reach conduction band, they leave equal amount of holes behind. So, n is equal to p. So, I can equate equation 1 to equation 2, right. So, I can equate this equation to here. Note a small change, that instead of E f, I have written E f I. What is E f I? It is the Fermi energy level or the Fermi level in an intrinsic semiconductor, that semiconductor which has not been doped as yet, where the Fermi level is located. Okay. So, E f I tells me the Fermi level in an intrinsic semiconductor, right. Because I have equated these two, now I can divide also. So, I can write N v over N c is nothing but exponential of minus of E c minus E f I minus E f I minus E v. Okay. So, this should be plus, and this is equal to k T, right. So, this is what is going to give me a small arrangement of a mathematical arrangement, give me this expression. From this, if I take natural log, I can get E f I. Okay. So, E f I Fermi level in an intrinsic pure semiconductor is equal to E c plus E v by 2 plus half of k T natural log of N v over N c. Okay. This second term here which you are seeing, this is generally very small. Why? If you remember the expression for N v, it is equal to 2 into 2 pi effective mass of electrons k times T divided by h square to the power 3 by 2. Right, this should be, this is the expression for N c. Okay. And for N v, it is 2 into 2 pi effective mass of holes k T by h square to the power 3 by 2. See, more or less all the terms are common except the effective mass. If you divide N v over N c, it is only directly dependent to the effective masses. So, you can also write that E f I is equal to E c plus E v by 2 plus 3 by 4 natural log of hole effective mass and the electron effective mass. Okay. If the effective masses are equal, this term becomes 0. Even if they are widely different, even if one is very large as compared to the other, this term is going to be very small because of this natural log here, which basically means that your intrinsic Fermi level is nearly equal to E c plus E v by 2. On the energy scale, if this is E c and this is E v, okay, this is energy scale. So, E c plus E v by 2 is nothing but the middle of this. Okay. It is known as mid gap energy. So, we can say that in an undoped semiconductor, in a pure intrinsic semiconductor, the Fermi level lies more or less near the center of the energy band gap. Okay. So, this is for a pure case. Let us see what happens in a doped semiconductor. Again we start with the same equation of carrier concentration. Both Fermi level and carrier concentration are interrelated. Okay. So, one depends on the other, one affects the other. Okay. Now, we know that in a doped semiconductor these concentrations are not equal. If Fermi level and carrier concentration are related, and if electron and hole concentration changes with doping, it is obvious that EF is also going to change. So, the location of Fermi level also changes. From the equation of electron concentration, I can say that E c minus E f is this, and from the hole concentration, I can say that E f minus E v is this, okay, which basically means if you see this equation here, if P goes up, your E f minus E v will reduce. Here, if N goes up, E c minus E f will reduce. Okay. So, on the energy scale, if this is your E c, and this is your E v, initially your Fermi level was in the middle, we call it E f I. If you increase N, this E f I will shift upwards, if you increase P, this shift downwards. And what is affected by N and how N and P can change? If you change the level of doping, if you increase pentavalent doping, N goes up, so your E c minus E f reduces. If you increase the trivalent doping, P goes up, then you reduce E f minus E v. So, the idea here is that your Fermi level for pentavalent doping in an N type semiconductor shift upwards, in a P type semiconductor it shifts downwards. Okay. So, this is what the effect of doping is. This is what is written on the screen. I have just said that if electron concentration goes up in an N type semiconductor, E c minus E f will reduce, which means Fermi level shifts on the upwards. Okay. Same happens in a P type semiconductor. If hole concentration goes up, E f minus E v will reduce, which means the Fermi level is moving downwards towards valence band. And how these concentration will increase? If you increase doping concentration. Okay. So, now we know the movement, we know the effect. Let us just try to quantify the amount of shift. E f shift towards E c in N type devices, it shifts towards E v in P type devices. Okay. I just want to quantify how much is this shift is. For an N type device, as I said earlier, with doping you add an imbalance in carrier concentration, but charge neutrality is maintained. So, negative charge is always equal to positive charge. Okay. So, negative charge, number of electrons, okay, number of electrons is equal to number of holes per unit volume plus the doping concentration. ND here means number of donor atoms or ions, you can say, once they are ionized per unit volume. Okay. You can also call it ions also, once they donate an electron, they become positively ionized. Okay. So, ND is number of donor atoms or ions per unit volume. Once they donate electron, they become positively charged. So, negative charge is balanced by positive holes and positive donor ions. Okay. So, I should write here, instead of atoms I should write ions, because they are positively charged. Okay. So, N is nearly equal to ND. In a extrinsic semiconductor, majority carrier concentration is determined by doping. So, N is nearly equal to ND, and using law of mass action, P is equal to Ni square by ND, because N dot P is equal to Ni square. Okay. So, P becomes equal to Ni square by N, and N is equal to ND, right. Similarly, for a P type semiconductor, your positive charges, holes, are balanced by negative electrons plus negative acceptor ion density. those atoms which accept an electron, they become negatively ionized. So, these are your acceptor ions per unit volume. Okay. So, positive charge balanced by negative charge, majority carriers are holes. So, P is equal to Na. Use law of mass action to get minority carrier concentration, N dot P equal to Ni square, which means N is equal to Ni square by Na. So, what is the conclusion? In donor, if increase in donor concentration Nd shifts Ef upwards, increase in acceptor concentration shifts Ef downwards. Mathematically, this shift is represented by delta Ef equal to Ef minus EFi. This is Fermi level after doping. Okay. And this is Fermi level before doping. Okay. This is before doping. In an N type device, this is represented by this equation here. Okay. This is for an N type device. Always remember that the formula remains same, whether it is N type or P type, you will note it with Fermi level after doping minus before doping. That is the shift. That is how you mathematically quantify the shift. In N type devices, this is Boltzmann constant times temperature Kt, natural log of N over Ni. Ni is intrinsic carrier concentration. Okay. In P type devices, this is given by this ln Ni by P. So, you see majority carrier concentration determines where your Fermi level shifts and how much it shifts. So, this is the amount of shift. Now, this is directly related to your carrier concentration. Okay. Finally, we have quantified the shift. Okay. So, this is how you quantify the shift in Fermi level. This basically assumes that all your dopant atoms, whether donor or acceptor, they are fully ionized, 100% of them are ionized. Just in case they are not fully ionized. Okay. So, if they are partially ionized, the majority carrier concentration will still depend upon doping concentration. Okay. Fermi level and carrier concentration are interrelated, we have already seen that. So, Fermi Dirac function again can be used to estimate carrier concentration in partially ionized semiconductor. Okay. In that case, we write if there is not 100% ionization, if your donor atoms are not fully ionized, all of them have not donated electrons, if your acceptor atoms are not fully ionized, if they have not fully accepted all the electrons. Okay. In that case, your carrier concentration N, number of electrons per unit volume in conduction band, is equal to Nd plus. What is Nd plus? It represents the concentration of ionized donor atoms. Whole concentration is equal to Na minus the percentage of ionized acceptors, and this is given by this expression here, where Ed represents the donor energy state, already explained, and Ea is the acceptor energy states. A small term extra is introduced here, Gd and Ga. These are nothing but degeneracy factors. At a particular energy level, you can have electrons with opposite spin, and in valence band you can have something called a heavy hole band and lower and a light hole band. Because of that, Gd, degeneracy factor in N type devices is 2, Ga, degeneracy factor in P type devices is equal to 4. Okay. So, with this we come to the end of today's lecture. We have completed the topic on carrier concentration. Carrier concentration is highly dependent on doping, it is dependent on temperature, it is dependent on energy band gap for the pure case. For the doped case, it is dependent upon the doping concentration, and Fermi level is a very good indicator to see how your carrier concentration varies in a semiconductor.